Good morning, students. I welcome you to a new class in physics today, in which I continue with magnetism. Okay, and today we are going to study about what is a magnetic field of a magnet. From the name, it is very clear. It is the area around a magnet in which its magnetic strength could be felt. In simple words, a magnetic field is an area around a magnet in which its strength could be felt. Okay, now how do you define it? It is defined as the space around a magnet in which the needle of a compass rests in a direction other than the geographic north south direction. Okay, and remember, children, that magnetic field is a vector quantity. Now, in order to understand this in a better way, I have a demonstration for you. Here, children, I have taken a bar magnet, okay, and I have placed it on a white sheet of paper. Right, I have another white sheet. I have two white sheets of paper. I take one white sheet and I place the bar magnet on the white sheet of paper. Right, I have done this, and I cover this magnet with another white sheet. Right, so the magnet is lying below this white sheet, and here I've taken some iron fillings. Now see what I'm going to do. I'm going to sprinkle these iron fillings onto the white sheet, and the magnet is below it. Remember, the magnet is below it, kept below this white sheet. Okay, children. Now you can see that as I'm sprinkling the iron fillings, they are forming a typical pattern. And when I tap this, I slightly tap it, Why do I tap it? So as to, define it in a proper manner. Now see, look at it. What can you see, children? You can see that there is a particular pattern of lines formed. And these lines are more crowded near the poles and less in the center. And you can see this, I'm clearing it out. This is the magnet. And these are the magnetic lines of forces, which you can see. Right, children? Okay, so what is this? These are the magnetic lines of forces. And this is the area around the magnet in which its magnetic field could be felt. So that is called as the magnetic field of the magnet. Now, the same experiment, I can perform it in slightly different way. Now I'm keeping the iron fillings. Now what am I doing in the other way? I'm taking the bar magnet again. This time I'm trying to sprinkle the fillings right next to the bar magnet straight away. Now you can see, children, as the iron fillings are falling, what is happening? Again you can see that a typical pattern is formed around this magnet. Again, you can see these are the magnetic lines of forces. These are known as magnetic lines of forces. You can tap it to get a special arrangement. You can see it. Similarly, when I take a horseshoe magnet, now this is a horseshoe magnet. And in case of a horseshoe magnet also, if I want to, if I start throwing the iron fillings around it, again you can see that here also there is a typical pattern which is formed around the horseshoe magnet. Now this also shows the magnetic field lines around the magnet. Okay, children. Now if I discuss with you that we have seen what are magnetic field lines, and now I discuss with you the what are magnetic field lines. So magnetic field lines are continuous curves. You can see here as I speak, they are continuous curves, okay, which are found around a magnet. And whenever I draw a tangent at any point to this magnetic field line, it gives us the direction of the magnetic field. Now let's see how. See, right close to it, I draw the bar magnet. Here is my bar magnet, which I have taken over here. This is the north, this is the south, suppose. And you can see that the magnetic field lines are formed in this way, from north and then like this in the form of concentric rings like this. Right? Similarly, they are formed in concentric rings. Now, when I draw a tangent to these magnetic field lines at any point, I get the direction of the magnetic field. Okay, so this is how we define the magnetic field lines. We say a magnetic field line is a continuous curve in which the magnetic field, when I draw a tangent to it, the tangent depicts the direction of the magnetic field. Okay, so these are the magnetic field lines around the magnet. These are the magnetic field lines around the horseshoe magnet, around the bar magnet. And if I draw a tangent, that gives the direction of the magnetic field. Now let us look at the properties of magnetic field lines. They are closed continuous curves. Yes, definitely they are closed continuous curves. You can see they move from one point and to the other. They are not open, they are closed. They are directed from north to south, always outside the magnet. Okay, that is when they run. See here, look here. The direction is from north to south, outside, right? I have marked it with arrow. But inside it runs from south to north because it comes like this. Okay, so inside the magnet, the direction is from south to north, but outside it lies from north to south. Okay, and when I draw the third point, when I draw a tangent at any point on the field line, it gives the direction of the magnetic field at that particular point. Okay, so that is point number 3. 4, they never intersect each other. They are always parallel. They are crowded near the poles because the poles are the places where the maximum strength of the magnet exists. They are parallel lines. They never crisscross each other, and they are equidistant. Okay, and they behave like elastic rubber bands. So these are the properties of the magnetic field lines which are obtained around a bar magnet or a horseshoe magnet. Okay, and these are the properties which you are supposed to learn, right, children? Now I move on to some figures which I have drawn for you, and these figures actually represent plotting of magnetic field lines around a bar magnet. You can see I have drawn around a horseshoe magnet, around two magnets. They are bar magnets, but they are placed such that the unlike poles are facing each other, and two bar magnets where like poles are facing each other, children. So when they ask you to plot magnetic field lines around a bar magnet, it looks like this. They are concentric rings. They are parallel to each other. They are equidistant. They are more crowded near the poles. You can see they are more crowded near the poles. They are parallel to each other. They are in a direction from north to south outside and from south to north inside. Okay, and they are equidistant, right? And they behave like elastic rubber bands, and they never intersect each other. Now here you can see, because the unlike poles attract, so you will get magnetic field lines in this manner, and because like poles repel, so you can see that it shows repulsion, right? So these are the diagrams which you should know. Okay, fine. I hope you've understood it. Now we move on to the next topic, and that is, you remember, children, I have mentioned this before also, that our earth behaves like a huge magnet itself. And if anybody asks us for evidence to be given as to how the earth behaves like a magnet, or our earth has a magnetic field around itself, if we want to explain this, we can explain it with the help of these 3 facts. The first fact is that when you suspend a magnet freely anywhere on the surface of this earth, it will always point in the north-south direction, such that the north of our magnet will point towards the geographic north of the earth, and the south of our magnet will point towards the geographic south of the earth. And in order to understand the first evidence in a better way, I have drawn a diagram for you, children, and I want you to be very careful as I explain you certain important points here. You can see I've drawn the earth, right? The figure of the earth. This is the geographic north pole of the earth, and this is the geographic south pole of the earth, and this is the equator of the earth, right? You are already aware of this. Then I have drawn a magnetic axis in pink, and this magnet is the earth behaving like a magnet. You know, the earth behaves like a magnet such that the south of the magnetic south pole of the earth points towards the geographic north, and the magnetic north pole points towards the geographic south. And it is correct. Why? Because we know unlike poles attract each other. So naturally the magnetic south will point towards geographic north, and the magnetic north of the earth's magnet will point towards geographic south. Now, when I suspend my bar magnet anywhere on the surface of this earth, this orange is the magnet which I have suspended. Now, my magnet, gets aligned with the earth's magnetic field. Right, children? That is, the north of my magnet will point towards the magnetic south, and the south of my magnet will point towards the magnetic north. And it should be so, because it is coming under the influence of the earth's magnetic field, right? Because it is closer. And in doing so, that is the north of my magnet towards the magnetic south, and the south of my magnet towards magnetic north. In doing so, the north of my magnet faces the geographic north of the earth, and the south of my magnet faces the geographic south of the earth. So this evidence proves that the earth behaves like a magnet, due to which my suspended magnet comes under the influence of the earth's magnetic north and south, and in doing so the north faces the north and the south faces the south of pole, that is the geographic. Okay children, so this is evidence 1. Now we move on to evidence number 2, which you can do it on your own children. You can also do this. You need a soft iron rod, or you can use a iron rod, and you have to dig a hole under the earth a little deeper. Okay, and you bury the iron rod inside the earth in a manner that it should be buried in the kept in such a way that it should point in the north south direction of the earth, right? Now it is to be placed in the north south direction, and you cover it with mud again. You take it out after a month, and when you take it out, to your surprise, that iron bar will be behaving like a magnet for few days, maybe few weeks. Why? Because it has become a magnet under the influence of the earth's magnetic field. Because it was placed under the earth, so this iron bar starts behaving like a magnet under the earth's magnetic field. So that is again an evidence that our earth has a magnetic field. Then the third point is that a magnetic needle rests making different angles when suspended at different places on the earth. Now, in order to understand this evidence, again I will explain it to you with the help of a diagram which I have drawn over here. Now you can see children, I have used 2 colors here. You know what is it? Let me explain you first. This is the earth, right children? This is the equator, and this is the magnetic axis of the earth. This is the magnetic north of our earth. This is the magnetic south of our earth. And here I have drawn magnetic needle, that is this compass needle. This magnetic compass I have placed at different positions like this, at different positions of the earth, right? Now what I want to show over here is that when the magnetic needle is placed in such a manner that the magnetic compass needle is placed here, it is understood that the north of my magnetic needle, compass needle, will point towards the magnetic south of the earth, definitely. Okay, because unlike poles attract, and as the needle is moving from this point to this point, it is going to take a 90-degree turn, and then from here to here another 90-degree. You can see when the north was facing the south, here the south is facing the north, so it is a total 180-degree turn. And again from here to here, again it takes another 180-degree. And you can see I have used different colors. The orange represents the north and the pink represents the south. I have shown it over here. So the most likely questions asked is, give 2 places where the magnetic needle becomes vertical. The magnetic needle comes in a vertical position at the magnetic poles, children. Which is the magnetic pole, children? These are the magnetic poles, right? This is magnetic pole. This is magnetic pole of the earth's magnet, and the needle becomes vertical over here, right? It is like this. And when it moves to the magnetic equator, see children, look at the pencil, like this it turns. Okay, so when the magnetic needle comes to the magnetic equator, it becomes horizontal. Then again it becomes vertical. Then again it becomes horizontal. So this way you should know, that is the evidence over here. See, this I told you that magnetic needle makes different angles and it points at different directions. Yes, of course it will do so, because it comes under the influence of the earth's magnetic field at different points, and therefore it is it is vertical at one point while it is horizontal at the other point. I hope you have understood this point. Okay, so I have given you 3 evidences, children, to prove that the earth also is like a huge magnet. 1, when we suspend a magnet freely, it rests in the north-south direction. 2, when you bury an iron rod under the earth, when it is brought out, it behaves like a magnet. And 3rd, the different positions of the magnetic needle. Okay, children? So, yes, we have discussed this. Now, I come to the last topic of the chapter, and that is neutral point. Now, let us look at what is a neutral point and what do you mean by a neutral point. In order to understand this in a better way, I have drawn 2 diagrams for you, children. And in these diagrams, I have tried to explain you what is a neutral point and how can you obtain a neutral point. You can see I have drawn two diagrams simultaneously because I want to have a comparison between the two. Here I'm depicting the neutral points with the help of a cross, right? You can see the crosses are up and down, the crosses are left and right. Now let's look at it. What does it mean? When I place my magnet, that is this bar magnet, when I place it in such a manner that the north is facing the geographic north of the earth and the south is facing the geographic south of the earth, in that case, the neutral points will be obtained on the left side and the right side of the bar magnet. And when I place it in the opposite manner, such that the south of my magnet is pointing towards the geographic north, see, I have reversed it, and the north is facing the geographic south. In this particular condition, the neutral points are obtained up and down around the bar magnet. Now, first of all, let's look at what are neutral points. And I hope you have understood this. What have I drawn? I have drawn magnetic field lines. And you all know it is from north to south. Here also I have drawn the magnetic field lines. Now, what happens actually, children? When I place a bar magnet, the area around the bar magnet has strong magnetic field. We all know that. That is, the magnetic field of the magnet is stronger. And the Earth's magnetic field, which is outside, is weaker. In this area around the magnet, the magnetic field of the magnet is stronger than the Earth's magnetic field. Now, as you move away and away and away from this bar magnet, the magnetic field of the magnet becomes weaker and the Earth's magnetic field tries to counterbalance it, and there is a point which is reached where the magnetic field of the magnet counterbalances the magnetic field of the earth, and there you get a neutral point. I repeat, magnetic field of a magnet and the horizontal component of the earth's magnetic field, when they become equal in magnitude but opposite in direction, you obtain a neutral point there. And at the neutral point, when you use this compass needle, when you place a compass needle near a magnet, it will have a fixed alignment. But as you move the compass away and away and away, and when a neutral point comes, the compass will rotate 360. It will not point in any specific direction, because neutral point is a point where both the fields, the magnetic field of the magnet and the magnetic field of the earth counterbalance each other, and the overall net magnetic field is zero. That is known as a neutral point. Okay, children, so it is very, very important for you to know that every time when I place a bar magnet, suppose if I keep a bar magnet anywhere, there is a magnetic field around it and there is a Earth's magnetic field also acting around it. But because the magnetic field of the magnet is stronger, so the Earth's magnetic field is not felt. But as you move away from a bar magnet, the magnetic field of the magnet becomes weaker and the Earth's magnetic field starts becoming stronger, and a point is reached where both counterbalance each other, and that point is known as the neutral point. Okay, I hope you have to practice these diagrams, children. They are very important. Okay, and I hope you have understood the concept of magnetic field lines. Okay, children, of course you have to plot, you should know these diagrams also. The evidences you should be able to explain with the help of these two diagrams, which are very, very important in order to explain the evidences. And of course, you should know, last but not the least, you should know what is a magnetic field, what are magnetic field lines, why are they considered to be vector, because they have direction, okay, and what are the different properties of the magnetic field lines. Okay, children, so please go through all these topics carefully from your book. Practice the diagrams also, which I have drawn. Okay, and any doubts when arise, please note them down and they will be taken up in the doubt class following this particular lecture. Thank you, children.